Welcome back to the deep dive. Today, we are doing something a bit focused, a rigorous technical analysis, really digging into just one source.
Right, a very dense one.
Exactly. It's the technical report from Tongyi DeepResearch, all about their new agentic large language model.
And we should be clear, this isn't, a quick look at some new features.
No, not at all. This report is, well, it's like a complete engineering blueprint.
Right.
For building an AI researcher, basically. An autonomous one designed for really deep information-seeking tasks.
That's a good way to put it. And for our audience, mostly ML and data science experts, the architecture here, the whole training pipeline, it really demands a close look. The model itself, they call it 30B-A3B, and it presents this fascinating engineering trade-off. It's all about efficiency.
Okay, tell us about that.
So while the total structure has 30.5 billion parameters, which sounds huge,
right.
Their key claim, the really interesting part, is that it only activates about 3.3 billion of those parameters per token during inference.
Okay, that's sparsity claim. That 30.5 billion total down to 3.3 billion active. That's where we need to start. Why is that ratio so important? Especially compared to, say, a dense model with similar capabilities.
Well, it comes down to deployment and speed. Inference speed, really, which directly hits the cost, the economics of running these deep research tasks.
Okay.
Now, assuming this is built on something like a mixture of experts and MOE setup or maybe some other sparse mechanism, the report is a bit cagey on the exact routing details.
Right.
That 7.5 billion number, that speaks to the model's overall capacity, the breadth of knowledge it can access. But activating only 3.3 billion, that drastically cuts down the actual compute needed for each step for the forward pass.
So you're sort of getting the knowledge capacity of a 30 billion parameter model, but the speed, the memory use, the VRAM cost, that's more like a much smaller, maybe 3 billion parameter model.
Exactly. And think about deep research. It's multi-step, multi-turn interactions, long chains of inference.
Right, it takes time.
So reducing the cost for every single token, that's absolutely crucial if you want to scale it up. This sparse activation lets them get much faster rollouts, which, as we'll get into, is fundamental for their RL training framework.
Okay.
It's a very deliberate design choice. They're prioritizing throughput for these agentic interactions over just raw, dense parameter count.
Got it. So our mission today, a professional, comprehensive, really detailed review. We're going to break down the architecture, this end-to-end training idea they have, the data synthesis, which sounds like the real engine here.
It really is.
And then, of course, the results, the actual experimental data that shows if this whole complex thing works.
And the core idea, the intended use case, is key. This isn't just another chatbot.
Yeah.
It's explicitly built for long-horizon, deep information-seeking research tasks. They're trying to move beyond simple Q&A.
The goal sounds incredibly ambitious.
Oh, it is. They state it pretty clearly. Augmenting, maybe even liberating human intellectual productivity. Automating those really complex reasoning and knowledge synthesis steps that, currently take human experts hours, maybe days.
And to pull that off, they needed some key advancements. What were those, sort of at the highest level?
Two main things, I'd say, that really change how you think about training agentic models. First, this unified end-to-end agentic training paradigm. It's got agentic mid-training, then agentic post-training.
Okay.
The idea is to build an agency systematically, not just tack on tool use later to a general model.
Right, bake it in from earlier on.
Exactly. And second, and this is even more critical, they developed a fully automated, scalable data synthesis pipeline.
And why is that second one so indispensable?
Because, as the report really hammers home, generating the right kind of data for deep research complex multi-step trajectories without insanely expensive human annotation. That's the bottleneck. That's the fundamental scaling problem for this whole field.
Makes sense. You can't just ask people to write out thousands of perfect research paths.
Precisely.
Yeah.
And the payoff for all this engineering, the benchmarks, just to give you a taste, Tongyi DeepResearch is hitting state-of-the-art results across really tough public benchmarks, Humanities Last Exam, HLE, BrowseComp frames.
Wow.
And often it's beating proprietary systems, which is, pretty strong validation for their whole approach.
Okay, let's start this deep dive into the training itself, this innovative end-to-end paradigm. Now, most of us know the standard LLM lifecycle. Huge pre-training, then instruction fine-tuning.
Right, the usual path.
When the Tongyi DeepResearch team looked at that standard approach, what was the core gap they saw? What was stopping those models from having real deep research agency?
They pinpointed it as a lack of agentic inductive bias. That's the key phrase. Your standard foundation models, they're pre-trained on, well, just vast amounts of text. And then they're instruction tuned for typical tasks, following instructions. The result, they argue, is models that are great at doing what you tell them. But they fundamentally lack the built-in structure needed for complex, multi-step, goal-oriented research.
So the model knows what instruction to follow, but maybe not how to strategically navigate that whole thought-action-observation loop over many steps.
Exactly that.
Yeah.
The data they're usually trained on. It's just too simple. It doesn't have research-level questions, doesn't have that multi-step complexity, or the structure of interacting continuously with tools or an environment.
Okay.
So if you try to just jump straight to heavy-duty agentic RL on a model like that, you run into problems, big optimization conflicts.
So.
Well, you're asking the model to learn general alignment and the grammar of using tools and complex exploration strategies all at the same time. It destabilizes the whole learning process.
Right. Too many competing goals at once. Which brings us to their solution, these two stages. Agentic mid-training and then agentic post-training. Let's start with the first one. Agentic mid-training, or they call it agentic continual pre-training, CPT. How does that bridge the gap?
Yeah, the agentic mid-training is like a progressive transition. It's designed specifically to inject a large amount of this agentic prior knowledge into the base model that's the Qwen 330B A3B base.
Okay.
It uses the standard next token prediction loss, nothing fancy there. But crucially, it's trained on a massive, high-quality data set of synthetic agentic trajectories.
So the data itself contains the agency structure.
Precisely. They frame the thought process, the action, and the observation as specific sequences of tokens. So the model learns the grammar, the structure of agency, just through statistical association, like learning any other language pattern.
So the base model is learning to predict that, okay, after a thought sequence, the next thing is highly likely to be an action sequence, like calling a search tool. And after that action, it expects an observation sequence. It's basically internalizing that React structure before it even interacts with a real environment.
That's exactly it. It cultivates these agentic biases early, gives the model a stable internal map of how goal-directed sequences work. And the report really emphasizes this. It makes the next phase, the post-training phase with the sensitive RL stuff, much simpler and more stable.
Okay, so that foundation is laid. Then we move to the specialized part, agentic post-training. This is where the model gets truly refined for deep research tasks.
Right. Post-training is fundamentally a scalable multi-turn RL process. But, importantly, it starts with supervised fine-tuning, FFT.
Why start with SFT?
SFT provides the critical cold start. It uses these curated, really high-quality synthetic demonstrations, we'll get into how they make those next, to teach the model how to imitate complex research workflows and how to use tools reliably.
Okay, so it establishes a baseline behavior.
Exactly, a stable baseline. It ensures the agent doesn't just flail around randomly when it starts the RL phase. You don't want it lost in the massive search space.
Right. But as we often see with SFT, just mimicking behavior cloning usually hits a ceiling, doesn't it? You get good imitation, but maybe not true exploratory smarts.
That's the classic limitation. And that's where the RL stage comes in to give it that extra push. The reinforcement learning part uses reward signals, feedback from interacting with the environment to actually refine the policy.
And why is RL better for this?
Well, it's key for a few reasons. First, RL is really the only way to get the model to explore genuinely new, complex strategies that weren't in the initial demonstrations. Second, it helps the model internalize goal-directed planning over really long sequences of actions. And third, it generally achieves better sample efficiency because it learns to prioritize actions that actually lead to high rewards in complex new situations. You can say SFT teaches the rules, RL teaches how to actually win.
Okay, this brings us to what, for me, is maybe the most fascinating piece. The heavy reliance on synthetic data. The report is pretty blunt. Manual annotation is basically impossible for these deep research tasks. Let's really nail down why for our audience, and what advantages does their automated pipeline give them?
Yeah, the core problem is the sheer complexity and density. Deep research isn't just answering one question.
Right.
It needs multi-hop reasoning, connecting dots between different sources, validating conclusions rigorously. Trajectories can involve dozens of steps. The data you need isn't just facts. It's about the process, the structure of successful research.
Okay.
So imagine trying to manually annotate that.
Yeah.
Tracing a complex research path from the initial query all the way to the final synthesized report. To get even a few thousand good examples, You'd need teams of PhD-level experts working for ages.
Yeah, the cost and time would be astronomical.
Exactly. It's just economically and temporally infeasible to scale manual annotation up to the level needed for training a 30 billion parameter model on these kinds of tasks.
So synthetic data isn't just a convenient shortcut here. It's more like a fundamental necessity for training agents on high-level cognitive work.
That's the argument, yes. And the advantages go beyond just cost. Automated synthesis makes it easier to scale up the complexity of the questions. And you can efficiently generate question-answer pairs where the answer is actually verifiable.
Verifiability is key.
Crucially, yes. And it allows for what they call targeted meta-capability enhancement. So they can analyze a research problem, break it down into cognitive skills planning, synthesizing info, managing memory, and then generate data specifically designed to train and test those individual skills.
That sounds powerful. And you mentioned the data flywheel concept earlier.
Right. As the agent gets better, it can actually help generate even better, more sophisticated training data for the next round of training. It's an iterative improvement cycle.
Okay, let's get into the mechanics. The agentic mid-training data synthesis, the agentic CPT data shown in their figure 3, they model the whole agent lifecycle, synthesizing data across 4 key steps. Walk us through that.
Okay, let's use a hypothetical example. Imagine the research question is something like, analyze the current economic viability and environmental impact of industrial hydrogen production methods in the European Union.
Pretty complex.
Definitely multifaceted.
Yeah.
Okay, step 1, question synthesis.
So this isn't just pulling random words together. It's anchored in what they call an entity-anchored open-world memory. The generator uses a structured knowledge base, entities like hydrogen, electrolysis, EU regulations, and their relationships. It generates the question, but it also embeds specific requirements into it. So for our hydrogen example, the question might be designed to force the agent to do multi-hop reasoning, connecting economic data with environmental data and maybe some numerical computation like calculating costs. The output is the complex question itself, ready to start a synthetic trajectory.
Okay, that's the starting point. Next, planning action. The initial strategy. Yes. For the hydrogen question, the plan might look like, step 1, search for major hydrogen methods like steam methane reforming, electrolysis. Step 2, search for current EU subsidies, carbon pricing. Step 3, use the Python tool to calculate the cost difference.
Right.
The key insight here is that good planning often predicts success. So they use other powerful LLMs to analyze the synthesized question and break it down. But here's a critical detail. They use rejection sampling.
How does that work?
They check the proposed plan against the entities and knowledge used to generate the original question. If the plan misses key concepts or goes off on a tangent, it gets rejected. This filtering step ensures the synthesized plans are actually relevant and high quality, not just shallow guesses.
Got it. Ensures the plan is grounded. Then we move to the core execution, reasoning action. This is where the agent digests information.
Right. This step is synthesized to mimic how an agent has to distill useful knowledge from potentially noisy tool outputs, like search results. It's a 2-stage generation process, guided by the question and whatever knowledge has been gathered so far. And the synthesized reasoning output, it goes through another strict filtering process. 2 filters. One checks the reasoning length, is it detailed enough for the question's complexity? And the other checks answer consistency. Is the extracted knowledge actually consistent with the verifiable facts related to the question? This keeps the synthesized knowledge path clean and reliable for training.
Makes sense. And finally, they explicitly model the decision-making action. Why synthesize this? Isn't it implicit?
Well, at every step in a long research process, the agent makes a decision. Search again. Synthesize now, use a calculator tool. These are often implicit choices.
Okay.
By explicitly modeling this decision process, they capture the optimal choice at each juncture. They look at successful demonstration trajectories, explore the potential actions the agent could have taken at each step, and then reconstruct the best path as a sequence of decisions. This reinforces strategic policy learning, ensuring the training data reflects good choices.
Wow. So this isn't just about generating questions. They're generating entire synthetic solutions, detailing every component of a successful research process. That must be how the agentic CPT phase really scales up the agent's general competence.
That's the idea. The final output data for mid-training is just a long sequence of tokens: question, thought action, observation, thought action, and so on. And the model just learns to predict the next token. By doing that, It learns the optimal thought-action observation sequences, making that whole React framework almost second nature before it even gets to the harder RL part.
All right, let's shift gears to the agent's actual structure. They went with the vanilla React framework, basic reason act cycles. Given all the complex agent architectures out there now, hierarchical agents, specialized planners, that choice seems, well, almost surprisingly simple. Why stick with basic React?
Yeah, it does seem a bit counterintuitive at first glance. Their reasoning seems quite philosophical, actually. They explicitly invoke Sutton's The Bitter Lesson.
Ah, the idea that scalable compute and data eventually beat complex hand engineering.
Exactly. The core belief is that complexity and power should come from massive, scalable training data and compute, not from intricate, potentially brittle, human-designed structures or elaborate prompt engineering. They favor a general, robust method like React because they believe specialized designs risk becoming obsolete as the models themselves get smarter intrinsically.
Okay, I have to push back on that a little, though. We just spent a good chunk of time detailing this incredibly complex, highly engineered synthetic data pipeline that basically orchestrates agencies step by step.
That's true. It's very sophisticated.
So if they're moving all that complexity out of the model architecture and the prompt and putting it into the data generation, are they really following the bitter lesson or just shifting where the complex engineering happens?
That's a fantastic point. It's the critical tension here. The paper implies that putting the complexity into the data synthesis, which they can control, scale, and verify, is fundamentally more robust than hard-coding it into the agent's architecture itself.
I see.
By keeping the policy architecture of the React loop simple, they argue the agent stays more general, more transferable to new tasks. The data pipeline is treated like a stable, external factory producing the right training material, while the core agent policy remains clean and general. It's definitely an engineering trade-off, prioritizing deployability and iterative data improvement over architectural complexity.
Okay, that makes sense as a strategic choice. Let's quickly formalize the React mechanism they use. It's reasoning, then acting, interleaved, building up a trajectory, H-love. But the big problem for any agent doing complex tasks is the context window limit, right? Especially for long research. How do they handle context overflow?
Yeah, that's the Achilles heel. If your research takes hundreds of steps just feeding the entire history architeller back in, eventually the context window fills up and performance tanks. Their solution is what they call the context management paradigm. It's formalized in equation 3 in the paper. And the core idea is Markovian state reconstruction.
Okay, break that down. What does that reconstruction actually look like? What minimal pieces does the agent see at each step? $2.
So instead of the whole messy history, the agent is conditioned on just 4 things. 1, the original question, which doesn't change. 2, an evolving report. This is crucial. It acts as a compressed memory. 3, the immediate context from the very last action. And 4, the observation it just received. So the policy update becomes about predicting the next summary, thought, and action based only on the previous summary, the last action, and the last observation. Symbate, sus plus 1, sysbit, st1 fi.
That evolving report, symbotet, sounds vital. Is it like a fixed vector and embedding, or is it text?
It's text, a dynamically summarized textual output. And critically, the model is explicitly trained both in SFT and refined in RL to generate this summary itself. There's a specific training mode, the context management mode, that focuses on this.
Ah, so it's learning to summarize as it goes.
Exactly. It forces the agent to take all the information it's gathered, synthesize it, and boil it down into a concise, useful textual summary. This does 2 things. Obviously, it stops the context window from overflowing, but it also enforces a really structured reasoning process. The agent has to prioritize, decide what's important, and discard noise at each step to create that summary process.
That really does mimic how a human researcher works, doesn't it? You don't reread every single paper you found from the start. You keep updating your notes, you're running summary.
Precisely. And because Savrotext is text, it has another benefit. It can be easily used in that heavy mode testing strategy they have, which involves multiple agents and a synthesizer. We can talk about that later.
Okay. And the quality of that summary poem must be linked to the learning signal somehow.
Implicitly, yes. If the agent produces a bad summary, that leads to a poorly informed decision in the next step, tau plus 1 at tau plus 1, which likely leads to a lower overall reward down the line. So the RL process has to adjust not just the actions and thoughts, but also the quality of the preceding summaries that led to them.
Okay, we've established training is heavily synthetic. Now let's focus on the data for that crucial post-training phase. This data needs to set a superhuman level baseline before RL kicks in. Walk us through the pipeline for this high-quality synthesis, the one in Figure 4. It sounds intricate.
Oh, it is. It's a complex, fully automated pipeline, specifically designed to generate QA pairs that are not just correct, but also have high uncertainty and complexity, really pushing the agent.
How does it start?
It starts by organizing knowledge. Graph construction. They build an interconnected knowledge graph using web data, random walks, isomorphic tables, basically structuring information. Then subgraph sampling pulls out small pieces of this graph to generate initial seed QA pairs.
But just sampling probably gives you pretty simple questions, right? The really clever part must be the uncertainty injection. How do they programmatically make the questions harder?
Absolutely, that's pivotal. They strategically increase the difficulty using a formal framework. They have these controllable atomic operations that they apply to the relationships between entities in the graph.
Can you give an example of an atomic operation?
Sure. Let's say an initial subgraph links Paris in 1920 to post-war artistic movement. A simple question might be, what art movement was in Paris in 1920? Okay. An atomic operation could be something like attribute masking and entity merging. Maybe it takes Paris, merges it with a similar entity like Lyon, and removes the specific year in 1920. The new, harder question becomes something like, analyze the key post-war artistic movements that emerged in major French cultural centers during the early 20th century.
Okay. That forces the agent to do more than just recall a fact. It has to search more broadly, maybe compare info about Paris and Lyon, and synthesize a more general answer.
Exactly. It systematically increases the required reasoning depth. They mentioned other operations too, like adding more temporal constraints or making the causal chain needed to find the answer longer. The point is, it's a systematic, programmatic way to escalate difficulty, giving them fine-grained control over the challenge level in the training data.
And having this formal approach must help with verifying the answers, too, since you know how the question was constructed.
Yes, precisely. That formalization is key for verification. They mentioned using ideas from set theory, possibly drawing on work by Tao and colleagues, to model the information-seeking process. This helps minimize reasoning shortcuts, control the difficulty scaling, and crucially allows them to efficiently verify if the synthetically generated answer is actually correct using algorithms, rather than needing slow, expensive human fact-checking. It ensures the integrity of the ground truth data.
Got it. They also talk about creating PhD-level research questions. How does an automated system reach that level of complexity?
It seems to be an iterative refinement process. An automated engine first creates some seed QA pairs that already require reasoning across multiple sources. Then, a dedicated question crafting agent takes these seeds and performs what they call iterative complexity upgrades. So it might take, say, 3 related but distinct questions, figure out the reasoning needed for each, and then synthesize a new, 4th meta question whose answer requires synthesizing the answers to the first 3. It compounds the difficulty and the level of abstraction needed. This ensures the data pushes the agent far beyond standard web Q&A.
Okay, so now they have this ultra-high-quality, complex, verified synthetic data. This feeds into the SFT phase, the cold start. Let's talk about the SFT mixed training paradigm they use, combining React and context management modes.
Right. They actually train the model using 2 different views or formulations of the same high-quality trajectory data. The standard React mode is what you'd expect. The input is the historical state up to that point, and the model learns to output the next thought and the next tool call. This trains the basic sequence of using tools.
And the context management mode, how is that different?
That mode is specifically designed to train the synthesis and summarization capability we talked about earlier. The input is deliberately constrained. It only gets the previous summary, the last action, the I1, and the last observation.
Okay.
And the critical outputs it needs to predict are the new summary, along with the usual thought and action. Training on data formatted this way specifically targets and strengthens the model's ability to analyze the current state and make strategic decisions based on a compressed view. It forces a model to get good at creating that summary, which is absolutely essential preparation for the RL phase where it needs to manage long horizons efficiently.
All right, now we enter the really high-stakes part, agentic reinforcement learning. This is where the policy gets pushed to its autonomous limits. The report stresses that a major hurdle was just managing the interaction speed, the bottleneck, with real-world tools. Walk us through the infrastructure they built for this, their on-policy framework in Figure 5. How do they make it stable and scalable?
Yeah, the bottleneck is a classic RL problem, especially with agents using external tools. Standard RL rollouts are often synchronous. The policy generates something, waits for the search API or Python interpreter to respond, gets the result, then generates the next thing. All that waiting time means your expensive GPUs are just sitting idle.
Right. Very inefficient.
Their solution is this on-policy asynchronous rollout framework. It's built using something called RLLM, which seems to be an internal, scalable RL toolkit they developed for large models.
And why is this asynchronous step-level approach better than the usual trajectory-level methods?
It fundamentally decouples the fast part model inference from the slow part waiting for external tools. They run two separate asynchronous servers online. One server just does rapid-fire model inference, generating thoughts and actions. The second server handles the potentially high latency calls to tools like Search or Google Scholar.
Okay.
A central handler coordinates everything, constantly processing outputs from both streams. So while one agent instance might be stuck waiting for a slow API call, the inference server is already busy generating the next step for dozens of other parallel agent instances whose tool calls just completed.
So it keeps the GPUs constantly busy, it overcomes that synchronous waiting bottleneck, and dramatically speeds up training, maximizes sample throughput.
Exactly. It enables massive parallelism, lots of independent agents interacting with the environment simultaneously and continuously.
That sounds like it exposes the learning process to all the messiness of real-world APIs, right? Search might time out, Scholar might have rate limits. How do they prevent that volatility from wrecking the learning signal? The report credits the unified sandbox. How does that layer provide stability?
The sandbox is absolutely critical. It's essentially a specialized fault tolerance layer wrapped around all the external tools. You're right, external API, chaos latency spikes, errors, weird responses can totally poison the training data. The agent might fail, and the RL algorithm wouldn't know if it was because of a bad policy decision or just because the search API failed.
So what does the sandbox actually do? What are the mechanisms?
It implements several things. Robust controls like proactive QPS constraints to avoid hitting API rate limits. Aggressive result caching, so if the agent asks the same search query twice, it gets the exact same result back instantly, which helps determinism and speed. It has automatic timeout and retry logic for temporary glitches. And seamless failover to back up tools or endpoints if one fails.
I see.
Essentially, it abstracts away the messiness. The policy interacts with what looks like a perfect, stable, deterministic set of tools, even if the real underlying APIs are flaky. This insulation is mandatory for stable RL.
Okay, that makes sense. Let's talk about their environment strategy. They use both simulated and real environments.
Right. They started with a low-cost, high-efficiency simulated environment. Think of it as an offline copy built using the 2024 Wikipedia dump and some local R key tools. This served as their wind tunnel laboratory, a place to iterate quickly on algorithms without hitting real APIs constantly.
Did the simulation work? Did it predict real-world performance?
That's the crucial claim, and they show data for it in Figure 10b. They say the reward curve they got in the simulation very closely matched the reward curve they saw later when training in the real environment with live APIs.
Wow, that's huge. If the simulation accurately reflects the real task dynamics.
It means they could do a lot of the expensive policy optimization offline, reliably. That's a massive advantage.
Okay, finally, the RL training algorithm itself. They adapted GRPO. They said the changes were pragmatic, focused on stability and efficiency, mostly because the sandbox was handling the environment's stability. What specific tweaks did they make?
It's a tailored version of generalized proximal policy optimization, GRPO. Key features. First, a strict on-policy approach trajectories are always sampled using the very latest version of the policy. Second, the reward signal, called RLVR, Reinforcement Learning Value Reward, is super simple. Pure 0 or 1, based only on whether the final answer was correct. No complex reward shaping for, say, format. They rely on the SFT stage to have taught good formatting.
What about the actual gradient updates?
They use a token-level policy gradient loss. This means the loss is calculated based on the probability of individual thought and action tokens, not just the final outcome of the whole long trajectory. This should provide a denser, more immediate learning signal. They also mentioned using a clip-higher strategy, which sounds related to ideas like data augmentation for policy optimization.
Can we unpack that clip-higher strategy a bit for our listeners? What does that likely entail?
Well, DA2 generally involves generating extra training data by augmenting or perturbing existing high-reward examples. In this GRPO context, a clip-higher strategy probably means they bias the gradient updates to more strongly encourage actions that perform better than the current policy's average expectation. It's a way to actively push the policy towards exploring actions that seem promising, helping it escape local optimas in the very discrete space of choosing tools or generating thoughts.
Okay, encourages exploration. And what about preventing policy collapse? They mentioned selectively excluding negative samples. How did they decide which failures to ignore?
This is a really practical and important detail. They noticed that sometimes the agent would fail not because of a bad decision, but because it hit an external limit, like a time limit on an API call, or the maximum allowed response length.
Right, an infrastructure failure, not a policy failure.
Exactly. Blaming the agent's thought process
Mm-hmm.
for that kind of failure contaminates the gradient. So they implemented a heuristic. If a trajectory failed, and the failure reason logged by the environment handler was something like hitting a length limit or an external timeout, that specific trajectory was simply excluded from the batch used to calculate the policy loss.
Smart. It prevents the policy from being unfairly penalized for things outside its control. Keeps the optimization focused on actual decision-making.
Precisely. It's crucial for robustness.
And this ties into the last piece, automatic data curation. How did the RL loop make sure it was always training on problems that were just the right level of difficulty? Not too easy, not too hard.
This is that dynamic feedback loop. They don't just train on one fixed data set. They maintain an active training set. Let's call it $. This set is filtered to exclude problems the current policy always gets right, too easy, or always gets wrong, currently too hard.
Okay.
Then, while training is running on a $, a background process periodically takes checkpoints of the improving policy and tests them against the original massive pool of problems, $. This identifies new problems that have now become moderately difficult, the Goldilocks zone, for the current agent.
Ah, so it finds the new frontier of learnable problems.
Right. And when the reward curve on the current active set $, starts to plateau, they refresh it. They kick out the now mastered problems and bring in these newly identified, challenging, but potentially solvable problems from the main pool $. This dynamic curriculum keeps the agent constantly learning efficiently and avoids the stagnation you often see when training on a static set of tasks.
Okay, so the culmination of all this intricate engineering, the data synthesis, the context management, the asynchronous RL sandbox is the benchmark performance. Let's look at Table 1. I mean, the headline result is pretty stunning. This 30B-A3B model, activating only 3.3 billion parameters, hitting state-of-the-art on tough English and Chinese deep research benchmarks. That alone feels like a powerful validation.
It really is. The numbers are impressive. 32.9 on each LE, 43.4 on BrowseComp, 70.9 on GAIA, a huge 90.6 on frames, AVG at 3, and it's consistently outperforming strong proprietary systems like DeepSeek v3.1 and Gemini DeepResearch.
So what's the core reason they pulled this off? Is it some magic in the model architecture, a revolutionary RL algorithm?
Honestly, based on the report, probably not. The fundamental reason seems simpler yet harder to execute. Mastery of data quality and training stability. They engineered the signal, basically. They made the training data incredibly high fidelity and relevant through that synthesis pipeline, and they made the training environment incredibly stable using the sandbox.
So the signal-to-noise ratio was extremely high.
Exactly. This allowed a robust, but perhaps not revolutionary, RL algorithm, like their adapted GRPO, to actually learn electively without being constantly derailed by bad data or flaky tool APIs. It's a triumph of careful, systematic engineering.
They also explored something called heavy mode, a way to scale up performance at test time. This feels like a really practical approach, getting more power without training an even bigger, dense model.
Yeah, heavy mode leverages that context management paradigm we discussed. The idea is simple. Deploy multiple parallel agents, none of them, all working on the same complex question. Each agent runs independently using the context management logic.
Okay.
And because each agent is trained to produce that concise textual summary report along with the tensor, you don't end up with impossibly long trajectories to combine.
Ah, right. The brilliance of the context management pays off here. Because the summaries are short text, you can feed all non-all summaries and answers into another powerful model, a synthesis model, without exceeding its context window.
That's the key enabler. The final answer comes from this synthesis step. Answer final. It intelligently aggregates the findings from all the parallel explorations. And Figure 6 shows it works. Heavy mode boosted performance significantly, getting up to 38.3% on HLE and 58.1% on BrowseComp-ZH. It validates using parallel search combined with smart aggregation via those context reports.
Let's dig into the detailed training dynamics in Figures 8 and 9. These really offer insight into how stable their RL process was.
Figure 8 is quite telling. It confirms the training environment setup worked beautifully. You see a clear, smooth, monotonic upward trend in the reward curve, continuing over hundreds of thousands of training steps.
No big dips or crashes?
Exactly. That sustained improvement shows the dynamic data curation was feeding the agent just the right level of challenge, preventing stagnation. And maybe even more importantly, the policy entropy stays remarkably stable throughout.
Why is stable entropy significant?
High or rapidly changing entropy often signals policy instability or collapse in RL. The fact that it's stable here confirms that their combination of the sandbox, the selective exclusion of bad samples, and maybe the GRPO adaptations successfully prevented the policy from destabilizing, which is a common failure mode in complex agentic RL.
Okay, now figure 9. We touched on this earlier, but it contains what might be the most provocative finding in the whole report, the capacity mismatch experiment.
Right. They trained 3 model variants, with 32 showed a clear downward trend in its average response length as training progressed.
It got shorter, even though the problems were designed for a 64K model. That seems backward.
It is counterintuitive, but it's the key insight. Because the 32K model was constantly attempting problems whose optimal solutions, found by the 64K curriculum, required more than 32K tokens, it kept failing and getting 0 reward on those long attempts. This implicitly forced the 32K policy to discover radically more efficient, more concise ways to use tools and synthesize information that did fit within its tight 32K limit. It learned to get the job done with fewer tokens because long, rambling paths were consistently punished by failure.
So the constraint actually drove efficiency. Can we speculate on what the 32K policy might have been doing differently?
We can infer some likely behaviors. The efficient 32K policy probably learned to generate those summary updates more frequently and make them more information-dense, rather than doing long, exploratory search sequences. It likely generated shorter intermediate thoughts to save tokens. And maybe it became more aggressive about pruning search results it deemed low utility early on. Essentially, the policy became more conservative and synthesis-focused because the environment punished lengthy exploration.
That's fascinating. The analysis of interaction test time scaling seems to support this idea that agent performance isn't just about raw token capacity.
Indeed. Figure 10a shows that for these kinds of research tasks, performance scales more directly with the number of allowed environment interactions or turns, rather than just raw context length or model size alone. Giving the agent more steps to think, act, and observe consistently improved performance on benchmarks like BrowseComp. It reinforces that mastering the RL interaction loop, making each step count, is critical.
Okay, and finally, just to confirm, this agentic training did generalize beyond just these deep research tasks, right? Figure 11 shows general benchmarks.
Yes, definitely. By integrating tool use effectively, the final agent showed huge gains over its non-agentic base model on math reasoning benchmarks like ANY25 and HMMT25, thanks to using the Python interpreter well. And it improved significantly on knowledge-intensive tasks like simple QA, leveraging the search tool.
So it supports their bigger thesis.
It does. It strongly suggests that effective problem solving across many domains is increasingly going to rely on these agentic architectures that tightly integrate reasoning with tool use and interaction with an environment. It's becoming a core part of AI capability.
Okay, let's try to synthesize the big picture here. What's the core technical insight we should take away from the Tongyi DeepResearch success?
I think the most crucial takeaway, rigorously demonstrated by this project, is that pushing the frontier of agentic RL, at least for these complex tasks, depended far more on nailing 2 foundational engineering pieces than on pure algorithmic convention. Those pieces were, first, data quality, achieved through that sophisticated, automated, verifiable synthesis pipeline, and second, training environment stability, achieved via the unified sandbox insulating the agent from real-world noise.
So robust engineering beat algorithmic novelty in a sense.
In this case, it seems so. They deliberately chose a relatively standard RL algorithm, GRPO adaptation, and made it work by feeding it near-perfect signal from high-quality data and a rock-solid environment.
Now, while the achievements are significant, the team was also refreshingly open about the limitations of the current work. What did they highlight?
They pointed out 3 main areas needing more work. First, context length. Even their 128K context window was apparently still not quite enough for the absolute most complex, long-horizon research tasks they envision. So a larger scale model is likely needed and probably in progress. Second, improving the fidelity of the final generated reports. Making the synthesized reports not just factually correct, but also better aligned with subjective human preferences for style and structure. That's more of a qualitative challenge.
Right, the human element.
And third, improving the efficiency of the RL training itself. They mentioned exploring things like off-policy training methods or partial rollouts, which could speed things up, but also introduce new challenges like managing distributional shift, especially since their current setup is strictly on policy.
So their future roadmap seems clear. Scale up the capacity, refine the output quality, and optimize the learning loop, all building on the stable foundation they've established. What's the overarching future outlook they described?
Their ambition is definitely high. They state a commitment to advancing agentic intelligence towards truly general-purpose agents, moving beyond just deep research to agents that can reason, plan, and act autonomously across many different domains with minimal hand-holding.
The dream of AGI, essentially.
Well, maybe a step towards it. They talk about developing a next-generation agent foundation model, one that deeply unifies reasoning, memory, and autonomy into a single, highly generalized system.
Okay, that sets a high bar for the field. Now, as we wrap up, let's circle back to that surprising finding from Figure 9, the capacity mismatch. Training the constrained 32K agent on a curriculum designed for the 64K model didn't just make it perform worse, it made it perform differently, more concisely, more efficiently. The policy learned brevity as a survival mechanism.
Right, that downward slope in response length driven by the capacity mismatch.
Yeah.
It's not what standard optimization practice would typically aim for or predict.
Exactly. So here's the provocative thought for you, our listeners. As the industry pushes towards democratizing agentic AI, getting these capabilities onto smaller devices, less powerful hardware, should we rethink how we design training curricula? Should we focus less on perfectly matching the task difficulty to the model's capacity and maybe more on strategically imposing a capacity mismatch like they accidentally discovered here? If doing so forces the agent to learn fundamental efficiency and conciseness, does that change how we approach scaling AI for widespread resource-constrained deployment?
It certainly shifts the goalposts, from just scaling raw capability to scaling intelligence per unit of compute. The huge challenge, of course, would be designing that mismatch carefully. You want to incentivize efficiency without just causing the constrained model to fail completely or collapse. But it definitely suggests a fascinating new dimension for optimizing agent behavior beyond just making them bigger.
Definitely something for all the ML engineers listening to think about this week. That concludes our very detailed technical deep dive into the Tongyi DeepResearch report. Thank you so much for walking us through this dense but incredibly insightful source material.
Always a pleasure. Great discussion.